Let's start by looking at something called a geometric series. We're going to take this function and express it as an infinite series. One thing that will help us is the geometric series formula, which states that 1 over 1 minus r can be expressed as an infinite sum, also written in sigma notation as shown. Now, how is this going to be helpful in this problem? Well, what I can do is take the original function and I can rewrite it so that it looks like 1 over 1 minus r. The first clever thing I could do is multiply this as x squared times a fraction where the numerator is 1. And another clever trick I could do is take the plus in the denominator and write it as a subtraction of a negative. And one might ask, well, why do you want to write a plus as the subtraction of a negative? Well, because if we can take part of our original function and write it as 1 over 1 minus something, then we can just call that something r and use the infinite sum formula for that expression. If you followed this, great. If you got a little bit lost, now would be a perfect time to hit pause and put all the symbols together in your mind and see how I did this. Now, we still don't have this expressed neatly as an infinite series, so we can do some cleaning up here. First, I can distribute the x squared into the sum, and then I can do a trick with the exponent where I raise both of those factors to the n power, and the algebra here is a little bit boring, but super easy to follow, and once you clean it up algebraically, you now have a new expression for your function, expressed as an infinite series. If you got lost in all the algebra, then hit pause and analyze the work. And now, effectively, what I've done here is taken a function that is not an infinite series and written it as one that is. And that's called using a geometric series to rewrite a function. A similar thing exists when we're asked to use a binomial series to rewrite a function. Suppose we were given this function here. We were asked to use a binomial series to express it as an infinite sum. Well, this is the binomial formula, which you essentially just memorize. I wouldn't spend a lot of time worrying about where it came from. It's very interesting where it came from, but I wouldn't spend a lot of time thinking about it. So once you've committed this to memory, there's some amazing things you can do with functions. Watch this. First thing that I'm going to do with my cube root is I'm going to write it as a 1/3 power. You'll recall that the cube root is the 1/3 power. Well, why would we want to do this? Well, because if our function looks like the binomial series, then I can simply note that in this problem, my m is 6x squared and my p is 1/3. And then I can just take the binomial series formula and plug in these expressions for m and p and get this. Now would be a good time to pause and analyze the work. Once you've made sense of this big mess, all it really comes down to is simplifying the terms. Now the work isn't shown here, but some basic high school algebra will show that these big, ugly, messy terms ultimately simplify to these terms. And what we've now done is expressed our original function, which was a cube root, as an infinite series, using the binomial series to do that. Let's take a look at this differential equation here. If you have probably solved differential equations like this in a different way than you're about to see. If you've been doing your work in order in this course, then you've already solved differential equations like this in the previous assignment. And there's nothing wrong with doing that in general here, except for the fact that the directions are asking us for a Taylor series approximation for the solution for y rather than an actual solution, which you would have been able to find on the previous lesson. So we're essentially going to take a problem we've done before and take a look at it in a new way. If we're being asked to have a Taylor series approximation for a function, one really cool trick that we can do is say, okay, well, this function is going to look like a polynomial here, or an infinitely many-term polynomial, as you can see here. So I've basically just used a, b, c, d, and e for the coefficients, meaning that a, b, c, d, e, f, g, h, and so on are some numbers that we don't know. But we're assuming that whatever the solution to this differential equation is, that function is expressible in this form for some values of a, b, c, d, and so on. So under that assumption, the first thing I want to do is use the initial condition, y of 0 equals 4, to find out what a is. If I plug x equals 0 and y equals 4 into this formula, it's clear to see that this equation reduces to 4 equals a. And now that we know that a is 4, I can replace a with 4. But in terms of solving for b, c, d, and e, we have to use a little bit of a trick here. What we're going to do is take the function y, which we still don't know what it is because we don't know what b, c, d, e, f, g, h, and so on are, is I'm going to take the derivative of that function. Hit pause and convince yourself I took the derivative properly. Now, why would we want to take the derivative of a function if we don't even know what that function is yet? Well, because of the following trick. I can take my original differential equation, here's the original problem, and I can get a new expression for y prime by just plugging in my assumed formula for y. Now what I can do is use some basic high school math and essentially multiply 6 plus x times the second polynomial function. And I'll get an infinite series essentially that looks like this. You again may want to hit pause and just verify all the algebra so you can follow along with what I'm doing. The next thing that I decided to do here is to collect like terms. Notice there are 2x terms, there are 2x squared terms, 2x cubed terms, and so on. So I collected them together. And again, you may want to hit pause here and confirm the math for yourself. Now that I've done that, it answers the question, why did I take the derivative of my original function in the first place? Well, by comparing these two functions together, we can see that each of the component parts of these infinite term polynomials, these Taylor series, that each of the terms have to match, and that will lead me to an infinite system of equations, the first four of which I've listed here. And now that I've made these comparisons, this system of equations in the right corner is incredibly easy to solve for. I did it on scratch paper, you could do it yourself, and these are the end result of that system of equations. And now that I know what b, c, d, and e are, I can take my original assumption about y, plug in those numbers, and I now have a Taylor series approximation to my differential equation here. Now, just to remind you one more time, this differential equation could have been solved another way to find an exact solution. You learned that in a prior lesson. But since they asked for a Taylor series approximation for the solution, then it suffices to only list the first 5 terms, or how many ever they'll tell you to list. They'll always tell you how to list it. And now I have a Taylor series approximation for my differential equation.